Lesson 7.3 is extending on what we talked about in 7.2 with representing combined probabilities with diagrams. And now we're going to look at the mathematical formulae that go along with this. So first I would pause the video and write down this set theory notation notes. So this is set theory notation. These are symbols that we use to represent situations and informal or formal words. So the first one here is an intersection. Intersection is represented with this upside down U. So this is A intersect B. The informal way is A and B. So this is kind of like an A looking thing. So it represents A. So that means that the events that occur in both A and B. So things that overlap between them. The next one is union. So this is A union B. The U is union. And that is our representation of or. But in math, or means the events that occur in A or B or both of them. So anything that occurs in A, anything that occurs in B, or anything that occurs in the intersection that occurs in the overlap. Complement is represented with this apostrophe here. So this is complement A or not A. So anything that occurs in your sample space but does not occur in event A. And then the last one is conditional. So this is A given B with a straight line in between. So that means the events A occurs given that we know event B has already occurred. So we know that whatever B is has already happened. So now what's the probability that A will also happen? So this first example says a student is chosen at random from this class. We have a Venn diagram that represents their survey answers. If E is the event that the students take ESS and G is the event that the students take geography, then we want to find these probabilities. So the first one, part A, says the probability of E intersect G. So remember, intersect means and. So we want to find the probability that you have a student who's taking both ESS and geography. And then the other way around, it says and the probability of G intersect E. So the probability that a student is taking both geography and ESS. So go ahead and pause the video and find those. So the first one says the probability of E intersect G and G intersect E. So the order doesn't matter. It's going to be the same thing. It's going to be the students who are taking both ESS and geography. So we're looking at the overlap in the circles of the Venn diagram. So there's only one student who's taking both of them. And I counted up all the total students, the 2, 2, 3, 1, and 3, and there's 11 total students who were surveyed. So 1 out of 11, or 0.0909. So go ahead and pause the video, and using your set theory notation from the previous slide, answer questions B through D. So for B, we have the probability of E union G and the probability of G union E. So this is or, so that means they exist in E, they exist in G, or they exist in both of them. So I always was told it's like a bucket, it catches everything. And again, the order is not going to matter on this one, they're going to be the same. So it's anybody who's in either of the two circles. So the only people that is not counted are these two out here that are taking neither of them. So the probability is going to be all 9 of these students out of 11, or 0.818. The next one says the probability of E complement, which means everybody who's not in E. So everybody who is basically not in this big circle right here. So the only people who are not in E would be these 3 who are only taking geography and these 2 who are not taking anything. So it's going to be 5 out of 11, or 0.455. So then for part D, we have the probability of E given G and the probability of G given E. So what this means is the first one says the probability of taking ESS knowing they take geography. So now we're only looking at these 4 students who take geography. Find the probability that they take ESS. So if you haven't already done so, go ahead and pause the video and do that first one. So we know they take geography, so we're only looking at the 4 students who take geography, and then given just those 4 students, what's the probability that they take ESS? Well, there's 1 who is also taking ESS. So you end up with 1 out of 4, or 0.25. So now that we've done that one, if you haven't already done so, go ahead and pause the video and do the probability that they take geography, knowing that they take ESS. So again, we know that they're taking ESS, so we're looking at these 6 students in here, and then we want to know out of these 6 students, what's the probability they're also taking geography? Well, again, it's going to be only that one overlap, so it's going to be 1 out of 6 or 0.167. So whenever you have the given, you're basically reducing your population to only whatever is in the given. So instead of the entire population of the whole class, we're only looking at the students who take geography or only looking at the students who take ESS. And then this was the only one that the order mattered. These two here, the order didn't matter. So here are some formulae to help us find these combined probabilities. So I would pause the video and write down these notes first. So the first one is combined events. That's your union, A, union B, so the event that A or B or both occurs. So the probability that A or B or both occurs would be all the probability that A happens plus the probability that B happens minus the intersection. So you have to subtract back off the ones that are shared, because if you add up A and you add up B, you're going to end up double counting that group in the middle, so then you have to subtract them back off. And that's also on your formula booklet. The next one is mutually exclusive events. Mutually exclusive events are events that can't occur at the same time. So knowing one occurs means you know the other cannot occur. And it also means that your intersection is going to be 0, so they don't have any shared events. So if you have a mutually exclusive events, then you don't have to worry about subtracting these back off. It's just you add the two probabilities. And then the last one, the complement of A complement, that's what that notation means. Everything except the outcomes in event A and A complement are mutually exclusive. You can't be both in A and not in A at the same time. And also, all probabilities have to add up to 1. So if you have the probability that A happens and you have the probability that A doesn't happen, that has to add up to equal 1. This next example says that Katerina is exploring the names of students in her class of 15 students, and she sorts the data and determines two sets. Set A are all the students who have 2 vowels in their name, and so then she lists out all the students who have 2 vowels. And then set B are all the students who have 3 vowels in their name, and she lists out the students who have 3 vowels. So go ahead first and pause the video and write a Venn diagram that represents this situation. So here's my Venn diagram. I have my outside sample space that represents everybody, and then I have my circle for set A, and I have my circle for set B. You could have also had them completely separate because there is no overlap between them. Then I have all the students who have 2 vowels in their name in set A, all the students who have 3 vowels in their name in set B, and then I also put 4 students out here that are not in either set A nor in set B because there was 15 total students, and there's only 11 listed out here. So there's 4 students who don't fit in either of these categories. So then given this information, find the probability that a student only has 2 vowels in their name, a probability that they only have 3 vowels in their name, and the probability of the intersection. And then using the information from the previous slide, decide whether or not events A and B are mutually exclusive, and then find the probability of the union. So I found the probability of event A, so I added up, there's 5 students who have 2 vowels in their name out of the 15 total students, so 5 out of 15, which is 0.333. For event B, there are 6 students who have 3 vowels in their name, so 6 out of 15, which is 0.4. And then for the intersection, you can't have both 2 vowels and 3 vowels in your name at the same time, so there were no students in the intersection, so 0 out of 15 or 0. So if you haven't already done so, go ahead and do parts B and C. So A and B are mutually exclusive because the probability of the intersection is 0. There's no overlap. They cannot occur at the same time. So because they're mutually exclusive, the probability of the union is just the probability of A plus the probability of B. So 5 over 15 plus 6 over 15, you end up with 11 over 15, which is 0.733. Basically everybody except for these 4 students who don't fall into either of the categories. So this next example continues from that first one. So Katerina is exploring the number of siblings of students in her class. So now she has a third set, set C, which is students with at least 1 sibling. So we're looking at set B from the previous example, students with 3 vowels in their name, and this new set C. So I want you to draw a Venn diagram that represents set B and set C, and then find all these probabilities down here, deciding whether or not events B and C are mutually exclusive. So I have my Venn diagram here with a group B being the group from the previous slide with 3 vowels in their name, and then group C being here with at least 1 sibling, and then we have 2 students, Oliver and Ricardo, that overlap, so they're in my middle, and then everybody else I put out here on the bottom because they're not in either group B nor in group C. So then the probability of being in group B, having 3 vowels in their name, is everybody who's in group B, which is 6 out of 15, or 0.4. The probability of being in group C, having at least one sibling, I added all this up, there's 6 of them out of 15, so 0.4. And the probability of B intersects C, so having both 3 vowels in your name and at least one sibling, is 2 out of 15, or 0.133. So the 2 that are in the middle here. So then whether or not they are mutually exclusive, B and C are not mutually exclusive because the intersection is not 0. There is an overlap here. They can both be happening at the same time, so they are not mutually exclusive. So then when you find the probability of the union, you add up the probability of everybody in B plus the probability of everybody in C, but we've double counted Oliver and Ricardo. We counted them once in group B and once in group C, so we have to subtract this intersection back off. So 6 over 15 plus 6 over 15 minus 2 over 15 is 10 over 15, or 0.667. So when events are mutually exclusive, you don't have to worry about subtracting the intersection back off because that's going to just be 0. But when they're not mutually exclusive, when there is a group that's in the middle here, you always have to remember to subtract them back off because we've double counted them. So here are a few more vocab words. I would pause the video and write these down. The first one is independent events, so events that occur that do not affect each other, and knowing that one event occurs does not affect the probability of another event. So if you know that you have independent events, then the probability of the intersection is the probability that event A happens times the probability that event B happens. So this would be like if you're flipping a coin and rolling a die. They're independent of each other. Flipping a coin is not going to affect the outcome of rolling the die. If I flip a heads, it's not going to change what I'm going to roll on the die. Dependent events are events that are obviously not independent, that one can affect the other. So that would be like if I'm pulling marbles out of a bag and I pull a marble out and I put it in my pocket and then go pull another marble out. That'll change the probability of the second thing happening. So those are not independent events. Conditional probability, which again we represent with this bar in between, probability of A given B. So that's the probability that event A occurs knowing that event B has already occurred. And the way that we calculate that is it's the probability of the intersection divided by the probability of whatever your given is. So probability of A given B is equal to the probability of A intersect B divided by the probability of B. Or if you rearrange these, the probability of the intersection is equal to the probability of the conditional times the probability of B. If you know they're independent from each other, then the probability that A given B happens is just the probability that A happens regularly. So this next example, we have a Venn diagram of students in a class who study Spanish and the number of students who study mathematics. So first we want to decide whether or not these are mutually exclusive. And then after that, we're going to talk about independence. So you're going to decide whether or not these two events are independent 2 different ways. The first way is by calculating the probability of they take Spanish and the probability that they take Spanish given that they take math. And then the second way is by calculating the probability they take Spanish times the probability they take math, and then finding the probability of the intersection. So using these probabilities and the information on the previous slide, determine whether these are independent, but before that, determine whether these are mutually exclusive and why. So the first part, they are not mutually exclusive because there is an intersection here. There are 2 students who are taking both Spanish and math, so the probability of the intersection is not 0. So for part B, I calculated the probability that they take Spanish. There were 8 students out of the 20 total who took Spanish, so 0.4. And then I calculated the probability that they took Spanish knowing they take math. So I'm only looking at these 5 students who take math because I know they take math. And 2 out of the 5 of them also take Spanish. So the probability that they take Spanish given they take math is also 0.4. So knowing that they took math did not affect the probability of them taking Spanish. So therefore they are independent. They're independent because the probability they take Spanish is the same as the probability of they take Spanish knowing they take math. So if you haven't already done so, try part B. You should end up with the same answer, but try proving it using the other method. So on this one, we wanted to prove it by deciding whether or not the probability of S times the probability of M is the same thing as the probability of S intersect M. So we found the probability of S to be 0.4. The probability that they take math, there's 5 out of the 20, so 0.25. So then I multiplied these two together and I got 40 out of 400, or 0.1. And then up here we had already calculated the probability of the intersection to be 2 out of 20, which is also 0.1. So because these two things are equal, they are independent. So these are just two different ways mathematically to prove whether or not two events are independent of each other. So here's a table that just kind of breaks down some common different situations. So complementary events, that means like one yes is happening versus no not happening. They're always mutually exclusive. You can't both happen and not happen at the same time. Dependent events, so not independent, are never independent. Obviously, you can't be both independent and dependent at the same time. Mutually exclusive events are sometimes dependent. It just depends on the situation. But independent events are never mutually exclusive unless you have a zero probability event. So if you know they're mutually exclusive, they are not going to be independent, and vice versa. So this next example, for a consumer survey, 2,371 adults are asked questions. An adult is chosen at random from those taking part. Event C is the event that the adult likes coffee, and event D is the event that the adult is called David. So you're given that C and D are independent events. So we're told that. Explain why this is the case. So think about the situation, and given the context, why would these be independent of each other, knowing the definition for independent events. So go ahead and pause the video and try that. So we know they're independent. If you think about the context, having a specific name is not going to affect whether or not you like coffee. So that's why they're independent events. So then they tell us that the probability of liking coffee is 0.8, and the probability that someone's name was David was 0.007. So given those probabilities and the fact that they're independent, we want to find the probability of C intersect D and find the probability of C union D, and then interpret those results. Once you've done that, determine whether or not C and D are mutually exclusive. So for the probability of C and D, we know they're independent events. So the probability of the intersection is just the multiplication of the two of them together. So the probability of C was 0.8 times the probability of D, which is 0.007. You end up with the probability of C intersect D to be 0.0056. And the interpretation is, if this is an and, this would be somebody named David who also likes coffee. And then the probability of the union, because the intersection is not zero, you would have the probability of C plus the probability of D minus the intersection, because we've double counted those Davids who like coffee. So you end up with 0.8 plus 0.007 minus 0.0056. So the probability of C union D would be 0.8014. And so these are people who either like coffee and or are named David. So they like coffee, they are named David, or they both like coffee and are named David. And then the last one, determine whether or not they're mutually exclusive. So now we have two ways to determine this. The first way is because no, they're not mutually exclusive because the intersection is not equal to 0. Or without even doing that, you could say that they're not mutually exclusive because we know they're independent. This last example, we have a Venn diagram that shows the number of students in a class who can speak Spanish, Italian, both, or neither language. A student is chosen at random from the class. Let S and I be the events. Choose a Spanish speaker and choose an Italian speaker respectively. So we have 6 probabilities to calculate here, and then given this information, determine whether or not S and I are independent with a reason. So go ahead and pause the video and do that. So finding the probabilities, the probability of S is 7 out of 28, or 0.25. The probability of I is 8 out of 28, or 0.286. The probability of S given I is 2 out of 8, or 0.25, because you're only looking at the 8 students who take Italian or speak Italian. The probability of I given S, you're only looking at the 7 students who speak Spanish, would be 2 out of 7, so 0.286. The probability of I intersect S is the 2 who know both out of 28, or 0.0714. And the probability of S times the probability of I, multiply 7 out of 28 times 8 out of 28, you end up with 56 out of 784, or 0.071. So they are independent, and you can use any of these three as your reason behind them. The intersection is equal to the two individual ones multiplied by each other. The probability of one given the other either direction is equal to just the straight probability of that first one. So the probability that they speak Spanish given they speak Italian is equivalent to them just speaking Spanish, and same thing the other way around. So this has been all of the formulas that go along with combined probabilities, intersections, unions, mutually exclusive, and independent events.